Thanks for coming to my session today. My name is Dan Smith. I primarily work on language features on the Java team at Oracle. Yesterday I gave a talk that was sort of a whirlwind tour of all the recent language features and things that are upcoming. Today I want to look at some of those things and also expand a little bit into some library and VM features through a particular lens of how do these features help work with immutable data. So some things I won't talk about, some things are really important for programs in current Java and in the future, important new features that make it easier and safer to work with immutable data. I'll start backing up even a little more. Let's just talk about objects. So if I put myself in the shoes of developers in the 90s when Java was launched, to me, these are the kind of the key big ideas of object-oriented programming that everybody sort of was ready to adopt then, and Java arrived and it was free and on the internet, and everybody ran with it. So some key ideas: take your variables and bundle them together with some related functions. Then put that bundle in memory somewhere and share references to that location so different components of your program can refer to that same entity, and call that entity an object. Create new objects with constructors, which configure the object to an appropriate initial state, and then protect the contents of the object so that the only way you can interact with it is through an advertised interface. Maybe call that a class. The interfaces can be extended, allow one object to support multiple types in hierarchy, and with all those tools, you can build an entire application out of just a bunch of objects. That's it. My sense of basically that's what object-oriented programming is. When we say everything is an object, here's the universe of objects. That means you've got objects that represent processes and state machines. You've got objects that represent your data, often immutable data that you're working with. You've got objects that represent functions and algorithms. They don't actually have any variables, they're just the behavior. Or maybe the variables are incidental to the behavior. The point is, these aren't all the same thing, but objects are powerful enough to capture what you need for all of them. So that's a big win. On the other hand, you sort of need to have a specific one of these in mind when you're thinking about a canonical object. And the designers of Java were kind of focusing on the process and state machine one. And so you get things like the default of every field is that it is mutable. And if you don't want to change the field, that's something you opt into. I want to focus this talk on just a subset of objects that represent immutable data. What do I mean by that? First, let's keep in mind that every object has its field values, which you could call its internal state, and then what it represents, which is external state. Those two things are not the same. Having fields with certain values does not define what you represent. What you represent is at a higher level of abstraction, and you use the fields to store information about what you represent. If an object represents immutable or models immutable data, the key idea is that it represents the same thing, fact, concept, information, something over time. It doesn't change in what it represents. Method results are always going to be the same. Call the same getter method 5 times, you're going to get the same result 5 times. There's no memory of what happened previously. I was reminded as I was thinking about this, when I was a college student and hanging out with my nerdy friends, we were playing this game of 20 questions or something. People ask you questions. You answer yes or no, and they narrow down what is the thing you are thinking of. And I had the bright idea that the thing I would be thinking of would depend on like how many words they used in their previous question. And so they'd ask me the different questions, and the thing that I was thinking of kept changing. I don't think they appreciated that. But that's the idea of having memory. If somebody asks you a question that changes what the thing is, that's not immutable data. Immutable data, once it's properly initialized, it can be freely shared across concurrent threads usually, because there's no interactions that need to be synchronized that's going to change what the thing is. Operations that map to other values create new objects without destroying existing ones. So if I have two numbers and I add them, I'm not going to return the original number modified. I'm going to create a third number. And the equals method is central in our idea of, I used the word same a lot on this slide. Equals is sort of the canonical representation of whether two things are the same. In contrast, other mutable objects, they have memory, they represent properties that change over time. The methods are like stimuli that affect the configuration of the thing, and as its configuration changes, you can observe those changes. Timing and concurrency, therefore, must be carefully managed, because the sequence of events that affect the object affect its eventual state. Key idea I want to take away here is immutable data is the entity being modeled. It's not the language feature being used. You can model numbers in whatever language you have, using whatever tools you have. But it's always still immutable data because it's a number. The language features can help make it easier. They can provide some integrity guarantees. They can encourage certain patterns. But ultimately, it's immutable data if what it represents is something that's immutable. A few extra notes about what this looks like in Java. When you create an object, how do you construct it? What you're going to do is take some fields and mutate them in order to set them to the appropriate values. Even if those fields will never change again, there's at least one mutation going on. And so it's a little more complex than to say that the thing is immutable. The thing starts out as a mutable object, and at some point you sort of declare, okay, now I'm not going to touch it anymore. It's immutable. Often, that's at the end of the constructor. It could also be later. When you think about the list and collection API, a common pattern with those APIs is to allocate a list, put some things in it, and then say, now I'm going to treat that list as immutable data and I'm not going to touch it anymore. Same idea with arrays. You allocate an array, go through a for loop, do some things to set it all up, and then it's sort of meant to be left alone. And so objects over their lifespan can become immutable because that's how I intend to treat them at certain points. Final fields are really helpful in this. What final fields say is this variable will stop being mutable at the end of construction. And that is a useful guarantee. But it is not the exact same thing as this this object represents immutable data. Sometimes things need to be initialized afterwards. Arrays, like I said, are a good example of that. Sometimes the immutable data has internal state that changes, but it doesn't change what it represents. So you could have like a cache that keeps track of something, that optimizes it for the next call, but doesn't change the result of the next call. And final fields can reference any object, and that object itself may not be immutable data. And if that's the case, then the fact that the field is final doesn't tell you, oh, well, this thing is immutable then. So again, just emphasizing, this is an informal property. It's a data modeling property I'm talking about. And tools like final fields are good to help, but they're not a substitute for actually thinking about what does this represent. What are some things that can go wrong when you're working with immutable data? Well, one thing is, if you're doing, like I said, create a list and hope nobody mutates it after a certain point, somebody might accidentally mutate it. And then all your assumptions about consistent results go out the window. Maybe you put it in a key of a hash map, and its hash code changes because you added something to it. And so it's no longer located where you expect to find it in the hash map. Initialization is tricky because, as I said, there's a period where it's mutable. So during that mutable period, if you accidentally share it with somebody who expects it to be fully formed and it's not fully formed yet, they can incorrectly assume that it's can be treated as immutable data, and it's not. Every object in Java comes with internal state that can't be ignored. So every object has a synchronization monitor. Even if I intend to just represent some immutable number, I can synchronize on that thing. Other users can synchronize on that thing. And that's a form of mutation. You're changing the state of the object from synchronized, from locked to unlocked, or vice versa. And as you make those changes, other people can interact with the object and observe what you've done. And so there are these fundamental features of the language that you're sort of stuck with when you're representing immutable data, and you can't really control people from depending on those features, even if they shouldn't. And then there's some squishier sort of inconveniences and overhead for using immutable data. When you have a record, say, with 5 fields, and you want to update one of them, you've got to pull out all the fields and make the update, and then allocate a new object with all those the other 4 are unchanged, but you have to kind of thread them through the plumbing of the creation. Whereas with mutable data, you just modify the field. And so that's one reason I think, especially in the early days of Java, people kind of avoided immutability and thought it was easier to work with mutable things. Another issue here is the perception that if you're creating new objects all the time, that's going to be bad for performance. That's going to add to memory management overhead. So it's better to make in place modifications. I don't think that is a good assumption to make, but it sort of became the lore, I think, as people were... Everybody thinks they're writing performance critical code all the time and doesn't want to do things that are better for the abstractions if they think that's going to come with a performance penalty. And in fact, the VM is very good at eliminating any performance penalty. Okay, to summarize, this is my list of what I think are best practices for Java. In classic Java, let's say up to 11. Think about this list. You could tell me if you think there's other things I should put on this list, but I think generally you should prefer final fields when you're modeling mutable data. You should use your constructors to initialize those fields. You should always override toString equals in hash code so that you're not exposing the identity of the object through those methods. You should provide a builder API or convenience methods if the object is large enough that it's not convenient to just construct it all in one go. Like I said, it's usually fine to just allocate lots of new objects, and that's not something you should worry about. VMs are good at managing memory. You should protect data with cloning if you need to. So if you've got arrays that you have to work with, clone them on the way in or the way out so that you know it's trusted and accidental mutation won't affect you. Or wrapping like collections on modifiable list. Take a mutable thing and protect it so that anybody who interacts with the wrapped thing can't perform mutations. There's some great APIs designed for immutability in the JDK. The string class out of the box was immutable, and that was a big deal. That made strings something that were simple to work with as compared to the C counterparts. Also, things like file, URL, those sorts of APIs were designed to be immutable. There's other examples like Java util_date that were designed to be mutable. So it wasn't all good API design, in my opinion, but there's a lot of good examples. More recently, Java NIOFile, Java time, the immutable list constructors, Java util optional. These are all things that sort of basic building blocks that build on immutable data. And in general, going with your immutable data, it's helpful to prefer declarative styles, functional styles. They seem to go together. If you have some values and you want to map them to other values, use a function with simple inputs, simple outputs, that kind of programming style. Anybody want to shout anything else you'd add to my list here? Best practices when you're working with immutable data? This is what came to mind as I was thinking about it. All right, I got two sections moving forward. This first section I think I'll be pretty brief on so I can focus on the other one. First of all, I just want to talk about what are the new features in 17, 21, 25 that improve the tools that people can use for working with immutable data. And then the section after that, I want to look to the future, talk about future features that are in progress right now that offer further more powerful tools. So very briefly, I touched on these in my talk yesterday. Let me just point out some of the features in 17 and 21 that will make your life better when you're working with immutable data. Switch enhancements. This comes with two things. First is the arrow form of switch cases. So rather than falling through as you list the statements that happen after the case, unless you have an explicit break, switch statements come with an arrow form that says just do this thing after the arrow. And then there's switch expressions as well. That's the one on the bottom. You can put a switch on the right-hand side of an assignment, and rather than mutating a field as you go, or mutating a local variable for each case, just generate a result that gets directly assigned, or you can do something else with it in your expression. Seal classes let you create hierarchies that are restricted to a specific set of subclasses. This is important as an integrity thing. It's also important for modeling data because it communicates to users of your class, these are the three kinds of things that you'll encounter. And so sometimes you can have a single class that represents your data. Sometimes you have a heterogeneous kind of mix of things. And seal classes give you the capability to have multiple cases, but still communicate to your users, there will only be these three cases. Records let you express the essence of what you are representing with your immutable data with a list of components. That's the thing in the parentheses. And in that case, the external state is the internal state. There are no fields here that you're going to directly declare and interact with. For a lot of simple kinds of immutable data, that's all you need. So if I want to declare a simple name with a first and last component, it's one line. Along with that one line declaration comes a constructor that accepts those two things. It comes with final fields. It comes with accessors for each of the components. It comes with toString equals hash code that is based on those components. And so that gets a lot of the things I had on my slide of best practices. You get them out of the box for free. Of course, you can customize aspects of this. So if you need to do some validation in your constructor or some special logic, that's allowed. If you need to override your accessors, there's a limited amount of a small layer that you can put between the field. This is my bottom example. So I have an int array field. I can clone it on the way out so that people aren't manipulating my internal data. But it still needs to have the same type. Yeah. And then patterns. So patterns let you query data in two ways. One is to check the types. So that's the first example, and then there's some there in the bottom switch. Looking at the different kinds of types that might be possible in this place based on the type of the expression I'm working with. And then the other thing that patterns let you do is deconstruct a pattern, or deconstruct a record. And so in the middle there's a record pattern, which tests both that the object is an instance of a class called this record, and it tests that it has two components. One is a string and one is an int. And along with testing, what patterns do is they bind variables that then let you work with the contents of the object you're looking at. So patterns are really powerful, especially when you start nesting. The fourth case there in my switch, I've got a nested pattern, so you can dig deep into your data, extract pieces of it, and then you bound some variables and you can go ahead with your logic. A lot of this lets you eliminate things like if-else and nested loops and things, and just get to the contents of your data. And then the key logic of what you're trying to do becomes clearer. Some advantages of using records. Immutable state is the external state. It's implicit and it's final, and you get all that automatically. It's easy to define, easy to instantiate, easy to query, easy to interpret. So with patterns, you can query it. Anybody who's looking at it can say, oh, I know what that represents. It has this name and it has these two components, and that's what the data is. And as I said, you can say what you want without focusing so much on how to get to it. Flexible constructor bodies is an enhancement to how constructors work. So there's two components to it. One is that a super or this call in a constructor can be floated downward in the body of the constructor. So you can put some other logic, some other statements before you get to the super or this call. The other aspect of flexible constructor bodies is before you get to that super or this call, you can set your fields. There's a lot of things you can't do that I've listed there on the right. So in this blue section, this is all code that runs before you get to the super call, and it is fairly restricted. There's not a lot that you can do with this, but one thing you can do with this is assign to its fields. And so that's what I've done here. Because this happens before the super call, then when I get to the orange code, the field is already set. And even if that super constructor does something dangerous with the field, for example, pass it to some validation tool that's going to look at this and maybe call toString or do something else with it, the field is already set. So in combination with final fields, it's really useful to set them during the early construction phase. Here's a broader illustration of how construction works. So the things on the left are the early phase of construction. The purple ones, the pink boxes, are the late phase of construction. In the purple phase, things are highly restricted. But as much as you can set up your object in the purple phase, when you get to the pink phase, when you hit object at the top and come back down from your constructor calls, as much as you can be initialized then, anything that happens in those pink boxes is protected from risks that I talked about earlier, like observing the field before it's been set. So here's some things I'd add to my list of best practices where we sit today with Java 26. Prefer record classes. Makes your life a lot easier if it fits for what you're modeling. Model heterogeneous data with sealed hierarchies using sealed classes and interfaces. Query and process the data with patterns and switch expressions. These are a really helpful alternative to needing to define a complex visitor interface that lists all the cases that need to be handled, and the user implements the interface and then hands it off to the class, which calls back into the right one. You don't need to do any of that if you're just using patterns and switch expressions. And prefer assigning fields during early construction. Avoid dependencies on this, because if you're working in that early construction phase, you're not going to be able to do things like invoke instance methods of this. Okay, that's what I'd recommend we do today. And then moving forward, here's some additional features to improve the tooling we can use to model immutable data. First thing I mentioned before, that it can be painful to create a slightly modified version of an object where there's a bunch of components and I just want to update one of them. Derived record creation, this JEP 468, is a tool to simplify that process. So what this thing is an expression with a with modifier and then some curly braces. And between the curly braces, the thing on the left-hand side of the expression gets broken down into its components, and you have local variables with the names of the components, and you're free to manipulate those in whatever way you want to. So here I'm negating the X or negating the Y. The bottom, I'm actually manipulating both of them. When you're done with the block at the end, then you're automatically going to get a new instance based on the updated values. So if I have a record and I just want to update one component of it, it's a simple thing to say with component equals whatever I want to update it to, and then the result of the expression is a new object. Abstract records are an enhancement to how records can be used. So today, every record extends the class JavaOne record, and every record is final. The feature here is the ability to declare a record that cannot be instantiated, but that shares some components from subclasses. So this is a common sort of example of this. I've got an expression which has different forms, and so every kind of expression shares a position, and that can be attached to the superclass record. And then each variant of my record has its own particular components that are relevant only to that type. So we can combine this with sealed classes. So I declare an abstract record, it's sealed, there's a certain number of variants, and then when I need to work with each variant, I can use a switch and cover all the cases. When I can just work abstractly with the location of an expression, I don't need to get to the individual records. What the feature here means is that there's a field. We still get a field. There's a constructor that the subclass can call, and the record is going to, the language is implicitly going to call the super constructor for that abstract record with a matching component. And so I don't need to wire up exactly how to pass one component to the superclass. It's all automatic. Early construction for records. So I talked about how we'd like fields to be assigned in the early phase of construction. We think it will make sense for all records to automatically be compiled in that way. Generally, records, you're not writing constructor code manually, and when you are, you're just providing little bits of validation, usually. And so the idea here is just change the compilation strategy, put the super call at the end, and then get all the benefits of early initialization. One of those benefits, by the way, is that the VM may be able to do optimizations on its interactions with those fields that it couldn't do when they were initialized late, because there's a new integrity guarantee here that the VM can rely on, that whenever it reads a field from a record that's compiled in this way, it knows that that field, that the result of the read is going to be the same as every future result of the read. Value records. I talked about how every object is stuck with a synchronization monitor, identity that can be observed with double equals. Value records let you opt out of those things. So you apply a value modifier to your record, and then all the instances are called value objects, which means they're totally indistinguishable from other instances with the same components. When I do a double equals test, I'm doing a double equal test on the field values. There's no monitor, there's no synchronization. And the JVM loves value objects. I've got an illustration of that on the next slide. But there's a whole world of optimizations the VM can do if it knows this is an object that doesn't have identity, and I am free to just strip it down to field values and rearrange those however I like. Most records don't need identity, so most are a good fit to be declared as value records. Here's just one illustration of what the VM can do. I've got an array of colors. This is kind of what it looks like in memory. The array is actually a list of memory addresses, and each address points to where it can go find a color object. Each color object has some overhead. Color objects point to the class that they belong to. With value records, I'm able to do something like this, or the VM is able to do something like this, where it takes that reference, which was a pointer in memory, and encodes the reference as just the data of the color, and there's nothing more to be represented. And so all those pointers going everywhere, all the overhead of all those memory accesses goes away. We just have the data embedded in the reference itself. The array knows what class this data corresponds to. And so as the VM is working with these components, when it reads them, it knows what it's getting and it knows how to interpret it. That's one example of a really powerful thing that value records can be used for. There's a lot of other tricks that can be used to get improved encodings of data in memory. Record patterns are being enhanced in a couple of ways, or we'd like to enhance them in a couple of ways. One is to support, when you're not testing, is this one of these things and does it have components of this shape? You already know what you have and you just want to extract things. On the top there, I have an example where an assignment or a variable declaration can assign an object to a pattern, and then the pattern deconstructs that entity. And so that's a simple way to get to the components without needing to drill into multiple method calls that extract the components. Another feature here is when you are doing a test, sometimes you want to test based on a particular value rather than a type. And so we'd like to add numeric literals, strings, enum constants, being able to use those directly within the pattern and just say, I expect this specific value, and if it doesn't match, that's not a match for the pattern. Okay, let's checkpoint here. So with all those enhancements to records, a few extra things we could say. One is when we're preferring record classes, they should be value record classes wherever possible. The second thing we can say is when we're working with heterogeneous data, we should consider whether abstract records are a good fit for modeling that data. Now, I've been talking a lot about records. As I sort of emphasized at the start, not everything can fit into that narrow box. There's a lot of immutable data in the universe that is expressed differently, that may have mutations in certain places, that may have caches and all sorts of different things. In general, it may have internal state that doesn't map directly to its external state. And so what we'd like to do is take many of these advantages of records that I just outlined and find ways for them to apply to other classes. You're not going to get all the same benefits of records. You're going to have to write more code. You're going to manage your own internal state. But if you can plug into some of these features, it can be really powerful. So an example of that is value classes. The value keyword can be applied to other classes that aren't records. What it means is all the fields of this class are implicitly final. All the fields need to be set early before the supercall. There's a special treatment of initializers and constructors in value classes where if there's an implicit super, that automatically gets placed at the end of the constructor to make this requirement easier to satisfy. Value classes can only extend certain other classes, abstract value classes or object, but they can implement any interface. They can provide any methods. They're objects in every way other than the fact that they've opted out of identity. And so all the things I said about value objects earlier that applied to records also apply to instances of value classes, including all the optimizations that the VM can do. If your class models immutable data and it doesn't need identity, then it may be a good fit for value classes. I think some people have viewed this feature as an optimization that you should apply when you're trying to hack your performance. And that's not the way we want to encourage people to see it. If you don't need identity, if the identity is going to get in the way and people are going to misuse your class instances because there's this extra bit of identity, opt out of it. It's better where it makes sense to declare a value class. Where are we at on time here? I've got about 12 more minutes. Okay, I think I'll be able to get through these other ones. So class and interface deconstructors. The idea here is to take those benefits of deconstruction and reconstruction that I talked about, like the derived record creation feature, the assignment to the components, patterns that are switch patterns that check for the components and nest patterns inside of each other. We'd like to give people all those benefits for other classes. It's not going to be the same capabilities as records, as I said, but we take the record syntax with the parentheses and the components in between them. And what this means when applied to an interface or a class is just, I have these components. These are sort of the essence of what this thing represents. And there are methods with the same name and type to get each of these components. So in my interface, I need to declare the 3 methods that match the 3 components. Having done that, any deconstruction pattern knows how to get the components. And so it can do the same thing it does with records. If I have a constructor with a matching signature, so in my color_impl class here, I've got 3 components in my header, and then I've got a constructor with those same 3 components. That's all the language needs to know in order to see how to deconstruct, hand that to a derived creation expression, and then reconstruct at the end. So I don't have time to spend a ton of time on the topic of serialization. But what I want to say is that immutable data is often something you're going to want to serialize in one form or another. And that the approach that traditional serialization in Java uses to achieve this is not very convenient. What it involves in this box class, so I've got a constructor that says, here's how you create instances of the box. Deserialization isn't going to use that. Instead, when I read a box out of a stream, it's going to create a box without touching any constructors. There's some magic there. The VM lets it create the box uninitialized. And then it's going to store that box in a cache and go on and do other work to deserialize the object. So that's going to involve arbitrary code that can go back and look in the cache and get the object, invoke its methods. This thing is out in the wild now, but it never got initialized. Then the last step is it will poke into that field and set the field value. So that's inconvenient. It's messy. It's really easy to miss that there's like an extra constructor here that you can't see. Records have a much simpler protocol. The components get deserialized, then they get passed off to the constructor. So similar to the last slide, we'd like to extend that to other classes. We'd like to be able to have a deserialization protocol that says deserialize the fields or the components, invoke the constructor, and then store that thing in the cache. Only publish it after it's fully constructed through a constructor. Then I know as a class author, all the instances that are out there have gone through my constructor, and I've been able to validate their data. There's also a coming marshalling API, which is intended to replace the serialization API, and that will use a similar protocol for construction. Another thing people try to do when they want to sort of indirectly create instances of immutable data classes is use reflection to get at the fields of get at a final field and turn off the final capability. And so the field has a set accessible method. You set it to true, and that means anybody can access it, and also anybody can mutate it through this field object. And then call set. So this is code that may exist today. The new feature here is to turn it off. So that when somebody says set this field, they're going to get an illegal access exception. They're not allowed to mutate the final field. This is long-standing behavior, so we can't just stop supporting it, but there's a gradual process to initially warn when this kind of thing happens. There are other better recommended ways to do what somebody's trying to do here, which is essentially to do their own deserialization, create an instance of C and configure it in a certain way. And eventually those warnings will turn into errors with the ability to turn on the legacy behavior with a command line flag I show there at the bottom of the slide. So there's not going to be a hard break here in most cases. In the case of value classes, there is a hard break because there's a hard requirement that the fields of a value class be initialized early and not changed. And so this isn't something you can do with value classes. I guess I didn't mention deserialization. Also, the legacy deserialization behavior doesn't work with value classes. And we want to move all of these behaviors to adopt functionality that depends on deconstructors and reconstruction. Okay, I'm just about out of time. I got a couple more slides. Lazy constants. This is a preview API you can use today, and at some point in the near future will become final, I think. What a lazy constant lets you do is have a final field that I don't want to compute right now. I'll compute it at some point in the future, and you do that with a lambda. Give it a lambda that tells it how to compute the thing, and then if anybody at some future point wants to get at it, they do so through a get method. Internally, it sets the value once, and then the value is always the same. Of course, you can kind of roll your own version of this. A lot of people will leave the field as null until they need it and then set the field. The advantage of using this API is, first of all, it's been carefully engineered so that issues like surrounding concurrency are handled appropriately. The lambda really only ever gets invoked once. And second, the VM knows about these things, and it can optimize them in a way that your own personal code wouldn't be able to be optimized. Because there's the invariant here, that once it is set, it's going to stay the same value. The last thing I'll mention is final arrays. Arrays have always been mutable. And so if you need to represent your data with an array, you can't say this is immutable in the same way you can with the fields of a class. So the new feature is to add the final modifier to an array creation expression. This doesn't change the type. It's still just a regular array type, but the internal representation of the array knows that any attempt to write to it is going to fail. Today, you write something, you get an array store check for a final array. You get an additional check that just says you're not allowed to write at all. This combines with the need to, I said everything's immutable at first, and then it becomes immutable. So how do I handle that with an array? The answer is I need a declarative way to describe what goes inside of it. And so a couple examples here are based on lambdas. And I have a list on the right of other strategies that could be allowed to derive your array from other data. Wrapping up, let's go back to my list of best practices one more time. So prefer value record classes. Let me add as a fallback, if you can't have a record or you can't use value, declare deconstructors, prefer value classes. Do as much of that as you can. Second, use abstract records. I said that before. Query with patterns and switches, prefer assigning fields during early construction. And then the last two I've added, use lazy constants. If rather than eagerly initializing something, you want to do it lazily. And prefer final arrays in declarative array creation, wherever you can. All right, that's all I've got. I've got just 1 minute for questions, if there's one or two questions people want to ask. And I'll point to links for the Valhalla project and the Amber project if you want to follow those newest features and see where they develop. I should say, I didn't put this caveat at the start, but of the future feature section, all of that's going to change. These are all in flux. Some of them are more mature than others, but we'd like to deliver something that looks like each of those features. Okay, any questions?
Could you create the final array from another ordinary array? So you're cloning it.
Yeah, that's one of the things there. So you might want to copy from another array and fill it in. Yeah, I didn't do it here on the left, but one of the things you could do on the right there is do copying. All right, thank you. Oh, one more question.
Records are shallowly immutable. I assume the same level for the value record they have on the list.
Yeah, that's right. So the question is, are value records shallowly immutable? Yes, there is no attempt to guarantee anything about whatever you're referring to. So if you want to model your immutable data, you need to be sure all the way down you're using objects that represent immutable data. Yeah, thanks. Okay, thank you.